Hello, my name is Alex Zabelski, and I'm part of Team 25, along with Alden, Clay, and Brennan. And we have been tasked to create a plant that is made for converting natural gas to ammonia. So ammonia has many purposes, the main ones being urea and fertilizer. Due to the increase in population and the increase of need for food, the need for fertilization is increasing at 3.5% per year. So ammonia is a market where the business will always be there to sell to. In addition, through the gas-water shift reaction in which we create ammonia, CO2 is also created. CO2 has a market that we are selling to for the food beverage industry. In 2007, the food industry, or the beverage industry, bought 300 million tons per year of CO2, so there's always a market in that. And due to the high fructose corn syrup and the need for people to have these kind of beverages, this market is still expanding today. So both of our products are within expanding economy. So our feed capacity that we have is 67,000 pounds per year of natural gas that we will be taking along and ultimately converting to ammonia with CO2 as a side product. So as you can see on this graph here, this is the composition of the natural gas that we start with. This big section right here represents methane, and it's 90% of our feed by mole. Some other smaller fractions which are also in our feed are ethane and propane, which can also be used in steam reforming to create hydrogen gas, along with inerts such as nitrogen and water. And then in addition to that, we also have things that we're going to need to get rid of, such as mercury and sulfur, or else they'll poison the catalysts. So our plant is scheduled to run 15 years at 8,000 hours a year. The extra hours of the year that the plant will not be running will be taking into account for maintenance and the catalyst restructure. So next, Clay is going to talk to you about our block flow diagram and walk you through the process of how we're taking this natural gas step by step through our plant to turn it into ammonia and CO2 as a side product.
Hi, my name is Clay Anderson, and I'm going to speak further about the block flow diagram. Our first loop involved the pre-treatment for all of our streams. On the top, you see the ion exchange membrane, which was used to remove the cations and anions of the feed water going into our steam reformer. This was done to prevent the fouling of the catalyst in the steam reformer and the water gas shift reactor. For our feedstock, we had a trace amount of mercury and hydrogen sulfide which had to be removed. In order to do so, we used activated carbon, which also prevented the fouling of our catalyst further downstream. So our second process loop involved the steam reforming reactor and the water gas shift reactor. To start, the steam reformer utilized a specific steam to carbon ratio in order to convert methane along with ethane and propane into carbon monoxide. The heat generated for this process was via a fired heater before the steam reformer, and the reactor was kept isothermal to react 60% of the methane and 100% of the ethane and propane. In order to abide by certain environmental standards, we decided to implement a high temperature water gas shift, which converted the carbon monoxide into carbon dioxide, which we ended up cycling that through our process and purifying to a food grade level, 99.5%, and being able to sell for an additional profit. Additionally, we sent the hydrogen through a palladium membrane, which was at 100% conversion, and the hydrogen went on to react in the next process loop. So the hydrogen comes through and is mixed with nitrogen that is bought at 100% purity and fed in with the hydrogen and then fed further into the Haber-Bosch reactor at 2900 psi. At the end of the Haber-Bosch reactor, we condense and store the ammonia product, which we achieved 122,000 pounds per hour of product at a 99.7% purity, which met all of the specifications.
Hello everyone, I am the other Anderson in the group. My name is Alden Anderson. I'm going to be talking to you guys a little bit about the capital cost of our project. So our capital cost consists of two items, the OBL and the IBL. The OBL is the outer battery limit. These are the items that are not included in the process itself. So this is going to be the things like the energy and the wastewater streams and this development in the site. The IBL, on the other hand, are going to be the items that are involved in the stream, in the process itself. These will include the heat exchangers, the compressors, and any item that will be seen in the stream.
That was perfect, but you should explain the graph.
Oh yeah.
But other than that, that was perfect.
I mean, so you just like merge them together, like how? Oh, you didn't.
Yeah, you didn't need recording. Hello everyone. I am the other Anderson in the group, Alden Anderson. Today I'm going to be talking to you guys about the capital cost of our project. The capital cost can be broken down into two items, the IBL and the OBL. I'm going to start by talking about the OBL. This is the outer battery limit cost of our project. This is going to include the things that are not in the project, the process itself. This will be the oil that we bring in for the heat exchangers, the treatment of the water that is expended, and the site development itself. The IBL is the inner battery limit, and that will be the things in the process itself. This will include items like the heat exchangers, the compressors, vapor liquid separators, and anything else that will be in the process. If you look at the graph behind me, you can see that the capital cost is broken down with 34% of the cost being in the OBL section and 66% of the cost being in the IBL section, with that being the dominant unit. Continuing on the theme of the IBL cost, I'm now going to discuss the different items that make up the $71 million of the IBL cost. As you can see, there are a number of items in the IBL cost in the pie chart behind me, but it is primarily dominated by two units. These units are the heat exchangers and the compressors. The compressors is the highest unit, with 51% of the IBL cost being from the compressors. This is because compressors themselves are inherently costly units. And as much as we try to limit the use of compressors in our process, we were unable to do so to an extent. This is because the Haber-Bosch process needed a very high pressure to function, a pressure of 2,900 psia. So with pressures this high, it resulted in a very high compressor cost. As for the heat exchangers, this is because of two reasons: the fired heat exchanger and the sheer volume of the heat exchangers that are being used. The fired heat exchangers are used to get temperatures above 1,000 degrees Fahrenheit, which is an incredibly costly process itself. And then we see large swings in temperatures as these 1,000 degrees Fahrenheit go down to 400 degrees, and then even lower to remove liquid streams, and then back up. This constant change in our temperature in the process resulted in a very costly heat exchangers. As for the OBL costs, this can be broken down into two units essentially. Of the $37 million that were involved in OBL, only 32 was done to the plant cost, which includes developing the plant for future use, and the rest was all for product storage.
Hello, my name is Brennan Bench, and I will be discussing the utility costs and the economic evaluation associated with running our plant and actually the feasibility of building this plant overall. So as you can see behind me, we have a graph of our total cash costs, where 64% of our total cash costs on a year-by-year basis, which is not including any capital at all, is all utility costs, which includes your low-pressure steam, high-pressure steam, as well as our fuel fire furnace, in addition to the electricity associated with running units such as our compressor, pumps, etc. In addition, we have 33% of our year-by-year costs, going towards raw materials such as natural gas, municipal water that will be purified into DI water to use in steam reforming reaction, as well as electricity coming into the plant. Only 3% of our year-by-year costs are fixed costs, such as the actual day-to-day maintenance of running the plant and things of that nature. As far as the fixed costs for our plant goes, while they are very much minuscule compared to the cost of utilities and the actual materials associated with running the plant, we do have about 88% of our fixed costs on a year-to-year basis going towards labor, with about $3 million of that going towards our actual operation and $4.5 million of that being in overhead. We decided that it would take 17 operators to actually run this plant, which would be essentially, we decided that it would be 2 operators per reactor and about a half an operator per each unit, so essentially 1 operator for every 2 units. The large bulk of our year-by-year costs come in utility costs, and of those, about 90 million of our yearly costs are attributed to both high-pressure steam and the fuel fire furnace. While we took every measure we could to try and mitigate the use of those 2 resources, such as recycling cooling water streams from several heat exchangers, as well as stationary heat exchangers using low and medium pressure streams, which are significantly cheaper than high pressure steam and fuel fire furnace, we still had to face a $90 million yearly cost, which is extremely significant. Beyond that, electricity is very negligible compared to our utility costs of the actual fuel, and our actual cost of the cooling water is significant as well. With that being said, it is important to note that the utility costs, being very dependent on things like high pressure steam, fuel fire furnace, and medium low pressure steam, are highly dependent on the price of natural gas. So, if the price of natural gas were to decrease by about 10%, while our plant is not currently economically feasible, our plant would become a positive investment, and that we would receive a positive return on capital investment. So, because the prices for all the utilities are natural gas derived, as well as the actual cost of natural gas itself, we could see profit at a different point based on the price of natural gas. So a large majority of the revenue derived from our plant will come from the production of ammonia, and with 122,000 pounds of ammonia being produced each hour, it leads to a yearly revenue of approximately $167 million. While this is our main source of income, we also have the opportunity to sell purified carbon dioxide that is removed through a pressure swing absorption in our first cycle of our process, and this can be valued at approximately $12.5 million, slightly bolstering those revenues and allowing us to increase our revenue in addition to avoiding the cost of trying to emit carbon dioxide into the atmosphere. A good way to measure the economic feasibility of our plant is to calculate the average after-tax rate of return. In doing so, you need to have a discount rate, which was assumed to be 12%, in which an alternate investment would be a better option. So, by calculating our revenues year by year and our incomes, we are found that we have a net present value of approximately $64 million, which is essentially the sum of all of our income over the 15-year operating period at the value of today, given that it is not invested. In addition, we are looking at total capital costs reaching about $83 million. So, based on the fact that the plant is bringing in $64 million over its lifespan and costs $83 million, we are seeing a negative $18 million return on capital, indicating that this is not economically feasible. In addition, our after-tax rate of return is negative 4%, and for this to be a feasible investment, we would have to see a discount rate or a rate of other investments being a 7% return for this plant to be considered.
Hello again. So to conclude, our plant is taking natural gas and placing it through multiple converters and the Haber-Bosch process ultimately to create ammonia with a side product of carbon dioxide. To create this plant is going to cost $108 million in capital, with 66% of that being IBL costs. Of these IBL costs, they are primarily from the compressor and the heat exchangers, as mentioned in our presentation. Although the compressors are expensive, they're something we can't get rid of because we can't liquefy nitrogen and hydrogen to make it economically feasible to feed that into the Haber-Bosch process, which would be the only way to reduce these compressors and still make this process feasible. In addition, the cash costs that we use are primarily dominated by the utilities, which are primarily dominated by the fuel fire furnace and the high pressure steam primarily. These account for 64% of the utility costs and $100 million a year. So reducing these costs would be necessary in order to make this plant economically feasible. Even with the $180 million in revenue that we're receiving, due to all of these costs, we're still resulting in a negative 4% rate of return. With the rate of return being that low, our recommendation is in order to move forward, you would have to address some of these problems and fix them in order to make this an economically feasible process, or it would be best to invest your money elsewhere and not build the plant. Investing your money somewhere in the stock market where you could get a constant rate of return might be a smarter plan until you can make this an economically feasible plan. I would like to give acknowledgements for all of the work that we've done. I'd really like to thank Penn State University for all its help in developing us as chemical engineers and allowing us to work through this whole process. I'd really like to thank Dawn McFadden for all the work that she has done in helping us along the process, whether it be giving us the material we need or teaching it to us. And I'd really like to thank our mentors, Berg and Walla and Tom Watson, for all their help in relating this to industry for us. Thank you.